Okay, so just a quick little bit of a quick brush through the book, and we just discuss chapter 1. We skip that. We go on to number systems, and very rapidly we'll skip that, and I'll just give you a little chat about number systems. The simplest numbers are the numbers that we count objects with. So if we find a basket full of apples, and we decide to count them, 1 would be the first number we would get, representing on a number line like this, 2, 3, and 4. And generally speaking, the number line isn't of much use to us for that. We just typically represent that set like so. Okay. Now, typically with sets, we say that the numbers don't need to be ordered, but of course we can put them in order. I'm just going to jump up to it. No, I won't bother. You'll eventually get to complex numbers, and they can't be ordered on any number line. But you'll only deal with them next year, so don't worry about that. Then we go on to Z, and what we do is we kind of want to clear the decks both sides and have this idea of these 3 dots mean it goes on forever, and have this idea that it can go on forever backwards and forwards. So there's 2 things to think about when you introduce Z. One is the reflection of the natural numbers backwards. -3, -2, -1, I'm putting in too many there. And the other thing is here, right here now, that 0 comes into it. Okay, I was coupling. I'll try to stop that camera rocking. 0 comes into it, so you're going both. You've non-positive integers, they're called, and then you still have your 1, 2, 3, and dot dot dot. That goes forever. So there are integers, and they are created through the subtraction within this set. Okay, if we do 2 minus 7, we get -5. So the process of subtraction does not close the natural numbers. So you get something like 5 minus 5 is 0, and we discover 0. Okay, and the process of... So that's fine, and then we move on and we say, well, that's it. We're still... with addition... excuse me, with addition and subtraction, we find that Z is pretty much closed. We call it a closed set under those operations, because we seem to realize that no matter which 2 elements or collection of them that we subtract and add to each other, we never get out of Z. Okay, and neither do we get out of Z from multiplication. But then division raises its kind of a nasty head, and it has this trait, an unusual trait, in that some numbers appear that aren't in Z, and they are but they are fractions. So we get numbers like -2/7 and 11/3, and numbers like 6, and you say, hey, what are you talking about? 6 is hardly a fraction, but it is a fraction, 6/1. Okay, and they are represented with the letter Q, and they cause a really strange phenomena that we haven't seen before in the other numbers, and that phenomena is that there's more than one way to represent it. Okay, when we're talking about integers, 3 is 3, and that's the end of the game. That's the end of the story. Okay. When we're talking about integers, the number -7 is the number -7. But when we end up with a number like 15/18, we realize that can be written as 5/6. Okay, and they're equivalent. They're the same thing. Okay, so that's really important, and the skill on the process. When arithmetic becomes generalized into algebra, it will be very important that we process fractions, and I think we'll be doing that this weekend with the revision we're doing right now. So that's the important thing. So basically, when we went from N to Z, we did so using subtraction, and there are 2 new traits, 0 and negatives, appeared. I'm just quickly going back over what we've discovered so far. Z was conserved under multiplication, addition and subtraction. But when we divide integers, we end up with Q. Now, there's one elephant in the room, and that is you're not allowed to divide by 0. Okay? So when we're describing Q, there is two ways you'll see it written. You'll say, now using set notation, we say Q is equal to, let me see, can I get this right? Any number P over Q such that, okay, P we will allow be an element of Z, but we do not need another Z, okay? We'll just let Q be an element of N. Okay, that avoids the dividing by 0, and we can put any negative, we can make it negative by using a negative thing. So it's best to consider the numerator to be an integer and the denominator to be a natural number. Okay, now sure enough, sometimes we end up with this as a calculation, and in particular then this explains to us, forces us to say, would we ever associate, that is two steps here. You can associate the minus with the top, or you can associate the minus, you can take it out and consider the minus to be negation. Negation is reflection in the number line. Okay, so say, look, take the number 7 over 2, but hey, guess what? We're not talking about the number 7 over 2, we're going back to minus 7 over 2. Oh no, so prime numbers are of course very important. And that topic will go right back to the natural numbers, and we will say we will only consider multiplication and the natural numbers, and we will realize that really from a fundamental point of view the composite numbers are not really that important as such, that there's a whole, that we only need prime numbers and multiplication to create all of the integers. That's basically what it's about. Okay, and to make a long story short, you just need to know that in the first decade you need 2, 3, 5 and 7, but it's a complete exception, and it's quite damaging in that ending with 2 and ending with 5 will never happen again. Those two multiplied together give us the base that we work in, and that's quite important, and they're very, very important numbers, especially when they're in denominators, because if there's nothing but 2's and 5's in a denominator, then we will find that terminates. It's a terminating fraction. And if there is anything else down here, any other prime number p down here, then it will not terminate, and there will be a repeating pattern, and just assuming there's some natural number up top here. Okay, 2, 3, 5 and 7. So where we go down here is, and this is a really important one, because we get 11, 13, 17 and 19, and from then on we're wondering, and the only candidates are these. The only candidates are 21, 23. I'm putting them in a box because they're not qualified yet. They don't qualify if they're composites. Okay, so if we can discover numbers, other numbers from above on our list that multiply to give this, then it's not a thing. So basically that basically happens in each. That's what you should be considering. In any decade you should be considering 4 at a time. But of course, things are really easy for us nowadays, because on our calculator we can take a number like 1001, put it in memory. Especially if you haven't, generally speaking, if you've done a calculation, let's say I do 7 by 11 by 13. Now I've done a calculation, so I see 1001 as the answer. So if you've done a calculation, you can always shift factorize, and of course we're not surprised with that because it factorizes back to that. What about 1003? Okay, and it's not prime, it's 17 by 59. But if you're just checking for primality, if you're checking to see if a number is prime, you need to put it in memory with the equal symbol. Okay, if you don't do that, you can't do shift factorizing because the calculator doesn't know what you're talking about. Doesn't have a number. It doesn't have a. Okay, the way it works is it needs the value in its memory bank. If you've made a calculation, it's already in there. That goes on up along. There's no exception. There's no decade. There's no decade with no primes until you with a full flush of primes after these two, until you get up to 101, 103, 107 and 109. You can check them yourself. And there are some numbers, 51, 91, that you really want to watch out for, and we'll see them over and over and over again. Then there is a thing called the divisibility tests, the test for a multiple of 3, test for a multiple of 9, and so on, test for multiples of 11. But we'll come to them organically as we need them, as we're doing problem solving. Otherwise it'll be a bit of a bore. So do we know all about prime numbers? Do we know all about prime factors? Yes, we do. And we're really get off scot-free if we can use our calculator for prime factors. Okay, so look, I'm going to stop. I have something else to do now, and then we're simply on page 2. I'm going to post this, and it's very little, but it's just getting the ball rolling, and we'll keep going on our. I'll basically talk you through what I want you to do for your revision.